First of all, I apologize. So I came down with a really bad cold over the last couple of days. As you can probably tell from my voice. Hopefully I'll make it through this class and the next class and the review session tonight. So I may not be able to speak by the end of the day, but I got some like generic daytime cold and flu relief. Don't do it. I'm not exactly sure what it's trying to do to me, but it's not pleasant. So anyway, and it hasn't been alleviating too many symptoms. But all right, so welcome back to, excuse me, and if I start coughing, if I actually pass out, if you like dial 911 and then like come up and if you know CPR, I don't think that'll happen. So it's hard to believe we're all only on day 2, right? It feels like we started class like forever ago, but we're actually only on day 2. I know a lot of you guys have already started homework 1, which is great. Some people have already submitted it, and we can talk about more details of that. Did you have a question in particular?
Yeah. So in Comp 11, when we submit, we get like a sort of immediate preliminary grade report. Is that the same one we provide for this class?
You won't get a grade report, but it'll say that all your tests passed. So that's the difference. It'll tell you which tests failed and passed, and if they all passed, it says congratulations, they all passed. And if they didn't, then you'll see which ones didn't, and it actually gives you the code that failed as well. So, yeah, it's a little different, but just try providing, you'll see. Okay, all right. So let's do this today. We are going to. There's a ton of stuff on here. First things first, as I said last week, there is a review session tonight at 7:30, and that review session is just if you've never done C++, like you came in and you didn't study or you didn't take Comp 11, I think this will be a little bit like below those who finished Comp 11. Like if you did Comp 11 and you did all right, you're still welcome to come by, but it's probably not going to be too much new stuff, right? But if you've never done Comp 11, if you're a Java programmer or a Python programmer or something, you can stop by. I will post that online as well, so you can watch that online. Labs start next week. Sign up is today at 6 p.m. I think I said this the other day. If you want to be guaranteed to get your time, the lab that you really need, then you should sign up right around 6 p.m. because they tend to go pretty fast. This is the website that you need to go to. It is this website right here, www.cs.tufts.edu/tilde/mole/lab15. Okay, and that please sign up for a lab. Just like in Comp 11, you can switch labs during the semester if there's space available, but there's really only 22, maybe 23 spots available in each class. If you don't get in the lab that you desperately need because your schedule is so squished that you can't find another lab, email me and we'll figure something out. Okay? If there's no labs that you can go to, then we've got other issues. But hopefully everybody will be able to go to something. Okay? All right. Let's see, what else do we want to talk about? This is a kind of a side note. If you happen to take notes and you have good handwriting, see me. I've got an offer you can't refuse. But after class, if you happen to say, hey, you know, I take notes every class, I'll be here every class, and I want to take notes, and they look pretty nice, I'll make it worth your while. All right, so just see me if you could. All right, we're going to do what I call the UNIX Tip of the Day. And you'll see these kind of often. I try to do about one every other lecture or so. And then an Eclipse Tip of the Day. Anybody still having trouble with Eclipse? A couple people? OK, if you are, either post something on Piazza or go to office hours or see me. Just email me. We'll figure it out. OK, everybody who's come to me so far with an Eclipse problem has eventually solved it. We've figured it out. So it's not the end of the world. We are going to talk about these things called interfaces, which you hopefully talked about in fairly good detail by the end of Comp 11. Then we're going to talk about these things called abstract data types versus what this class is all about, which is data structures. And we've got to differentiate between the two of those. Okay, I will go over a little bit more about homework 1. For those of you who've already done it and finished it, if you have more questions, feel free to ask. But I'll go over it kind of one more time. Then we'll talk about dynamic arrays in particular. So if you are a little hazy on this, this is going to be a fair amount of review for Comp 11 students, but we'll go through it really fast. And then finally, we'll talk about memory management. Did you guys actually, did you ever talk about memory leaks in Comp 11? Did you? Good, because the previous class never did. So if you don't know what that is, that's OK. We'll go over it again. But basically, the idea is when you ask for memory from the system for your variables, in many cases, you have to give that memory back by the end of your program, or it causes what's called a memory leak. It doesn't actually matter for your program, because when your program officially ends, the program gets all the memory back. But it's a good idea to keep track of your memory so that you can give it back when you need to. And then finally, we'll talk a little bit about testing your code, which I put some stuff on Piazza about that as well. OK? All right, any questions before I get going on some of this stuff? No? All right, ask your questions as we go then. OK? All right, so the UNIX tip of the day. Most of you guys, if you did Comp 11, you already know a lot of this stuff. I just wanted to show you a couple of commands that you should definitely get really familiar with on the terminal, right? ls, which is used to list the files in your folder, right? And there's a couple different, there's lots of flags for that. Cat, which is used to print out a file to the terminal. So if you just want to take a real quick look at a file, you can use this program called cat, or you could use a program called less, or you could use a program called more. They all do kind of the same thing. I believe cat came before more, but came before less. But they all kind of let you print these things out. Let me show you what I mean. OK? Let's see. So if we log in, and I got my password right. There we go. If we log in, and I just do ls, you guys should all know this by now, right? It just gives you a listing of your files, right? Fair enough, right? Well, turns out that you can type lots of different flags into ls, like ls-al will actually tell you lots of other information about it. It tells you these things called permissions. It tells you who owns the file. It tells you how big it is. It tells you when it was last modified, right? And it gives you all the details. The -a stands for all files, including the hidden ones. Anyone know what hidden files look like in Unix? They start with a period. If it starts with a period, it's a hidden file. Who knows why, but that's the way it goes. And then L means this kind of lengthy format. OK? All right, so that's the ls command, right? Let's see if I have, there we go. I'll use this file. There's a cat command, which stands for concatenate, which is like cat, and then I happen to have a file called trie.cpp, trie.cpp. And if I do cat and then trie.cpp, it goes boop, and it prints the whole thing out onto your screen. OK, just like that. If you don't want to try to quickly see it, because it prints really fast, you can just type, I like the less command. Less and more are pretty much the same thing. Less and then trie.cpp will stop it after it gets one page worth. And then you just either use the arrow keys to go up and down, or the space bar gets you to each next additional page. OK? And that's what you do. And then if you want to get out of this, you just type Q, and it takes you out. OK, so that's just a couple things about Linux that you might start to get used to. OK? All right. So that's the Unix tip of the day. So for Eclipse, has anybody found this error when they run Eclipse and it says workspace in use or cannot be created? Yeah, did you see the Piazza posts about how to deal with that? Yeah, there's a Piazza post that says to do the following, I believe. There we go. You actually type this command in here. It says /comp/15 public_html file /kill Eclipse. What that means is you get that error a lot of times when you're running Eclipse and then your internet connection goes down or something else happens to break your connection. And what it'll do is it'll kind of keep the Eclipse running, or keep a lock file or something that means that it thinks it's still running. So it says, oh, somebody else is using your workspace. So that will kill it, hopefully effectively enough to get you back up to speed. OK, and then you just rerun Eclipse. OK? All right. Anybody get to the point in Eclipse where this is way too slow, I'm just going back to Kate or whatever, or gedit or anything? Yeah, a couple people. Sorry. It's a little bit slow on wireless things, but that's all right. OK, so those are the big things. Now, let's talk about programming interfaces. OK? The interface for a programming language is the contract that you make, that the programmer or whoever defines what a class should do, and the programmer who writes the functions. OK? So the interface says, hey, your class is going to do this, 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 and this. And I don't care how you go about doing it. Like, I don't care what happens in the background. Now, do you care? Yeah, you don't want it to be super slow, or you don't want it to be wrong, obviously. But if it's correct and it's fast enough, who cares what's in the background? Okay? The interface just defines those functions that we're going to want to put in our program. So, for this first homework assignment, what you guys had to do is you had to define a bunch of dynamic array functions that met a certain interface for a list. Okay? For homework 2, you're going to do the exact same thing. In fact, it's going to be all the same functions, and you're going to have to do them for a linked list instead of a dynamic array. But the interface to the user is going to look exactly the same. Make sense? It's kind of like what we did on the first day in terms of how we actually went about doing our tests with all those different containers. It was the same sort of things in each container. You're going to do the same thing here. We normally put interfaces in those .h files, those header files, right? It's just the interface is kind of defined by the function definitions themselves. Okay? And sometimes we put comments that say, this should return this type of value. This should return this in this format. This needs to have a parameter that's in a certain format. Okay? Stuff like that. All right, questions on that? What an interface is? You guys talk about those in Comp 11? More or less? Yeah, all right. So here's an example, right? Card.h. If you guys were looking at your homework assignment, you'll see this. The text is a bit small. But what this has is, this is just the header file that says, hey, look, your card function, or your card class is going to have a bunch of these functions. It's going to be able to print a card. It's going to be able to get the suit of a card, set the suit, get the rank, et cetera, et cetera. And that's the interface. Okay? It just says, here's how you do it. Nobody cares how these functions are actually written if you're just using that function or that class. You just don't care in the big picture, right? Except for the speed and memory and that sort of thing. But you don't care otherwise. You don't say, hey, look, you have to do it this way. The interface just doesn't care. Okay? So here's just another example here. The interface up here just says it's the same card, right? And some people had questions about that, and they came into office hours and asked, what is the same card thing, right? The same card says, look, if a card is passed another card, it needs to return true if the card that it's passed is the same as the one that is that you're passing it to, right? And how do you do that? Well, you just check and you say, look, if it's an ace and the other card's an ace, and if it's a club and the other card's a club, then it's the same card, right? So that's the actual function. The interface is the top part. Fair enough? Not hard. Not hard stuff. Okay? Here's another example, right? Deal card from bottom of the hand, right? And I put a little comment in here. This one, I think, I wrote this function for you as well. But this deals a card from the bottom of the hand, which happens to be the first card in that array, and then adds the card to another hand, right? The interface says it's going to do that based on both the function definition and the comment. Okay? And it also says, look, the bottom is the beginning of the hand. Why? Because you had to pick one side or the other, and I happened to pick the beginning of the hand. As you guys become more like experienced programmers, you're going to start like having to think of these little things like that. Like if you say, OK, I'm modeling a deck of cards, and I've got my hand, well, you know, I have to define what certain parts of that hand are, right? So you'll start to think of those things as you go along. And it's always good to comment that, as you know from what we've talked about before, right? And then the add the card inserts it at the top of the other hand, and then it happens to return the card itself. Okay, so that's the interface is just the top part, and then the actual the function is down below. Okay, again, not rocket science. Okay. All right, here's another one. Has card, right? This returns true if the card is in the list, and this is the one that you guys had to write, I believe, which I guess I just wrote it for you, right? How do you do that? If you've got an array and you have to look through every card, you return true if that card happens to be in the array. All right? Somebody asked, well, wait a minute, what if there's multiple cards in there? Well, you still have a card in there, so you would return true. Somebody else asked, for remove card, do you need to remove all of the same card? No, you just remove one. We're not actually going to test when there's multiple copies of the same card in your functions. Okay? Questions on that? Not hard stuff. Okay. So let's go into, so we've talked about an interface. Okay, let's talk about what a data structure is. You finally get to this idea of what a data structure actually is. This is what this class is called. So let's talk about what it is. I mentioned all this the other day, right, on day one, that a data structure is just how we organize data so that we can use it efficiently. Okay, and that's what the data structure actually is. Okay, it's how to organize your data so that we can use it efficiently. We have these functions and methods that fulfill the interface requirements, and that's what the data structure actually is. Okay, for homework 1, data structure happens to be a dynamic array. Right? An array is a data structure. Right? Why? Because the array is kind of the part where you are doing the organizing. Okay? The array itself is the actual data structure. Another data structure is the linked list. Completely different way of thinking about it, right? We'll go into linked lists the next couple days, but you've done a lot of that in Comp 11, I know. But a linked list is also a data structure. Can you remove from the front of a linked list just like you can remove from the front of an array? Of course you can, right? So those are obviously, those are examples of data structures. And we are going to talk about a ton of different data structures this semester. Okay? Lots of different data structures. Okay? Contrast what a data structure is to what an abstract data type is. Okay? An abstract data type, which you'll just have to know kind of these terms, but an abstract data type is a data structure that's defined indirectly by the operations, which is not the same as the data structure. What is it very similar to? Right? The abstract data type is more or less the interface. Okay? So the abstract data type is just the interface that defines the abstract data type. Okay? They're kind of one and the same, right? If you want to say, I have a list, and I can add to the front of a list, and I can remove from a list, and I can see if a card is in a list or whatever, that's the abstract data type part of this. Okay? You write data structures to match abstract data types. Okay? The reason I'm going into this much detail is just to kind of hammer home the fact that you can do all these things in many different ways. Our job is to do them efficiently. And in some cases, our job is to do them not efficiently to show you that that's not a good way to do it in real life, like a linked list. Okay? I'll keep saying that a million times. Does anybody know who created the C++ language? Anybody know? A guy named Bjarne Stroustrup. And he's from, I'm going to get this wrong, and I forget exactly which country he's from. I think it's a Scandinavian country, but he created C++, and he has there's like a little 7-minute video. I might link to it I linked to it in the linked list. No pun intended. I linked to it in the linked list presentation. That he has this like 7-minute presentation about why you should never use linked lists. So anyway, we'll spend a day talking about it and then never use them again. All right. OK, so again, hammering this home, an abstract data type is just the list, right? That's the abstract data type. It says, I don't care how you do this stuff in the background, right? I just want you to insert at the head with a card for your list. Behind the scenes, you can make it a linked list. You can make it an array. You could make it some other type of ordered list. It doesn't actually matter, right? You're going to write the dynamic array, or you did already, for the dynamic array implementation. And then later, we're going to write the linked list representation. OK? All right. So more details about 1 and 2. I think everybody's started, most everybody's probably started homework 1. If you haven't yet, you're a little behind. But we created, and I went through this before, so I'll just breeze through it. We created 2 classes, right? This card class. And some people asked like, what are the order of these things? Is 2 always the first one? And for what you guys are doing, it actually doesn't matter. Like, that's already been written for you, right? So a lot of this stuff has already been written for you. So we put it in there so that you can go dig in and look at it. And again, if this was a really easy assignment for you, great. go dig in a little bit more and see how kind of the other classes are written. Like, look at them and say, oh, I get it. OK, there's this weird thing called an enum. Oh, I've never seen that before. Right? So take a look at that, and you'll get a little bit more details on those things. Okay? And then there's this hand, which creates the functions. And the hand has this private data member called list dynamic array. For homework 2, the hand class is going to be exactly the same, except it's not going to have a list dynamic array. It's going to have a list linked list, I think is what it's called. And it's the same as far as the hand is concerned. Why is that a good thing? That's a good thing so that if you're doing the programming, right, you can create the stuff in the background and change things and make them more efficient. And the end user doesn't have to learn anything new about the functions. Okay, that's why it's a good thing. Okay, all right. So let's see. We already talked about some of the things you can do with hands. You can deal them. You can add cards at the beginning and the end. You can remove them. You can shuffle a hand. I already wrote the shuffle algorithm for you. Take a look at that if you want. And if you want to make it better, go right ahead. You can order a hand based on a suit or a rank. You can check if a hand has a card. You can print a hand. All these functions, right, would go into if you wanted to write a game based on playing a card game. Right? This is exactly what you'd need to do all these things. Right? I mean, it'd be a little silly if all you could do is deal the cards and then not shuffle them. Right? That would probably be a bad thing. Right? If you didn't implement some of these things. There are definitely some things in here that I didn't implement. So you could certainly go back in and say, hey, in a card hand, you might want to show the card to your neighbor or pass a card to your neighbor or something, right? I mean, maybe pass to your neighbors a function or something, or swap cards between hands or something. Like you could create more parts of the interface, but for now, this is the ones we've created. Okay, we already talked. These are all the ones you have to do. Whoop. They're all in there. We will talk in detail about the expand function in a little bit, because that's going into more details about the actual dynamic array itself. Okay, all these functions are fairly straightforward. Let me know if you have any questions about them, or put a post on Piazza. I've already seen a lot of good posts on Piazza. Thank you to those who have been answering them as well. It's always nice. I can't always be up at 3 in the morning to answer your Piazza posts. Although I was last night because of this stupid cold. All right. OK, so as I said, the array function must meet the criteria in the interface, standard stuff, right? We've given you lots of comments. You can write your own tests. So speaking about tests, right? Let me go to the Piazza page while I'm thinking about it. Let me go to the Piazza page where I showed you the tests. I think I sent that one via email to everybody. Did everybody get that in email? The actual tests, or a couple of the tests? Why is my computer so slow? There it goes. OK, let's see. Tests. Let's see if this comes up here and shows to us. Testing. Here we go. All right. So here's an example of a test, right? A test is a very simple program to just do one thing with your stuff, right? With whatever you've created, your test is going to do that. So I just put a little a comment up here that says, hey, this tests this method, this replace at index method, right? And then you have your standard stuff, and then it's a main function, and you can just replace your main function with this one. Comment out your other one and replace it with this one. And you can end up, and then you just run this, and this just happens to create a dynamic array, a list dynamic array, right? It'll create a card. It'll insert at index 0. And if this crashed, you'd probably know where your problem was, right? And then it does some other things. It sets a new suit and a new rank and so forth. And it's really not a long program, right? But that's your test. Okay? Those kind of tests that are really short, no more than about 15 or 20 lines, write those for every program that you write, for all the little parts of the programs. Why? Because then you can make sure that your program's working efficiently, or working when you change something. The worst thing that can happen is when you've written a part of your program, and then you write another part, and that part works, but it breaks the first part. That's like the worst, because it takes forever to find those bugs. But if you're running tests every time, you can run all your tests again and say, OK, all these things are still working. And if it broke the other thing, then you'd be able to find out. OK, so that's what the tests are all about. OK, and if you do the provide for, if you actually provide your homework, you will see when the tests fail. Okay, it'll tell you the code that fails, and you can copy and paste that right into your main function and then debug it that way. So we'll do that for the first couple of assignments, so that you have the ability to do that. Okay, questions on that? Okay. All right, so let's see. We can also run other tests. Right? What does that mean? It means that I'm not giving you all of our tests. We'll tell you, we'll do most tests, but sometimes some of the TAs say, hey, this is an interesting test you didn't put in the provide. OK, we'll test it during the actual for the actual grading. You should be running your tests on as much of your program as you can. OK? All right. We talked about this before, formatting your code properly. So have you guys ever heard of obfuscated code? Have you ever heard of that? So next week I'll show you some demos of this. But there's actually contests that people run to say, give me a program that is completely ununderstandable. You can't understand it at all, and make it do something interesting. And people run these things, and you won't believe how crazy some of these are. Let's see if I can find one. Obfuscated C. There it is. Obfuscated C. Let's see. This is the International Obfuscated C contest, right? Let's see. Here's the winners of it. Oh no, I can't. You can't click on them. Oh no. Let's see. Entries. Oh no. Sorry, I can't do that one either. Let me see. Winners. The source code. Here we go. There we go. OK, let's see. Let's look at this one. That's not that bad, actually. It's not bad at all, in fact. That wasn't. No, wait till you see some of these ones. OK, let's see. I will show. Actually, this is the one that I'll show you next week. I think if I remember to download it. So, OK, right. So can you see the letters built out of this, right? But that's actual C code. Like, that's actual code, right? Now, if you're a human, you're not going to be able to understand that, right? Except if you're the guy that wrote it, I guess. But that's actual, like, legitimate code. Please don't make your code look like this, right? If you do, we won't be able to understand it, right? And it gets crazier, right? I mean, this is all, like, legitimate code. Yeah, kiss. I don't know what it means, but that's like legitimate, right? So it takes a special type of person to write this, I'll guarantee that. But anyway, I will show you some amazing ones next week. Okay, but anyway, point being, don't make your code look like that. Okay? All right. Okay. As I said, if you breeze through this assignment, think about expanding it. Now, here's some ideas on how to expand it. Okay, some people gave me some good feedback and said, hey, look, you should have put this in the actual assignment, how to make this program like more advanced, right? Anybody ever play poker? Not like in Las Vegas, but like play poker or some other like poker type game. There's a thing called a flush in poker, right? If you have your cards and they all happen to be the same suit, that's called a flush, right? And if you could, if you wanted to, you could write a little function that determines whether or not a hand is a flush. It's actually a pretty easy one to write, as it turns out. But there's other ones too. There's a straight, which means it's the numbers go in order, like 2, 3, 4, 5, 6 would be a straight in poker, right? You'd also have to worry about, you'd also have to think about the face cards and all that. So create a game, right, based on some of these things. If you wanted to go and create poker, that's like a pretty big, that's a pretty advanced game. But the interface we've given you gives you a good start to that. Okay. Anybody ever play the game War? It's a terrible game. It's like one of the worst games ever. My 7-year-old nephew loves playing that with me right now, and of course he also likes playing chess, and he almost beats me already. And I'm a terrible chess player, but he's actually pretty good for 7. But he actually likes this war game where you just flip a card, and the other person flips a card, and whoever's higher gets the card, and you keep doing that forever. The game like never ends. And you could create that game. It's a pretty easy one to create, right? So if you want, go ahead and do some of those kind of above and beyond. And we will give you bonus points if you put in the README that you did above and beyond, and we test it, and it looks cool. Okay? If you're still having a hard time with the assignment, please go to office hours. There's still office hours this week. If for some reason you're still having technical difficulties with either Eclipse or some other technical difficulty, email me. I will probably give you an extension. Okay? It's not a big deal. I don't think this necessarily needs an extension because it's not that hard an assignment, but for technical difficulties, absolutely. Okay? All right. Now, let's go into, this is a little bit more review again. Dynamic arrays. Okay? So we all know that an array is this piece of memory, right? It's a set of memory locations, just like up here, that are what? This memory location is like, let's say this is 0. This memory location happens to be the next one as far as the computer is concerned. Remember, a computer knows one thing. It knows that there's memory in order. 1, 2, 3, 4. And the computer will number this with much bigger numbers and mostly numbers in base 16 and all that kind of stuff. But this is what the computer knows. Okay, so we might as well talk about that one first. All right, in terms of data structures. There are addresses there, address 1, address 2, address 3, address 4, right? And you can access any one of those addresses based on your either pointer math or using the bracket notation. You guys all know this, right? But that's how it's set up. Okay? Data is in one big line, starting at a particular address, and it keeps going through the whole thing. This makes it fast. This makes it easy to access. This makes it random access. And it's a good place to start. And all computers these days have memory that looks like this. Okay? We can actually access the elements in a couple different ways, right? We can do this bracket notation, which I would suggest, which is the easier one, I think, right? Or you could use this pointer notation, right? So hopefully you guys have talked enough about pointers to know that asterisk x plus 3 means go to location x. If x points here, right? And this is a pointer in this case. X happens to be a pointer. If x points here, or here, right? The asterisk x plus 3 would be 0, 1, 2, 3, would be here, right? And in this case, it's going to be what? If we print out x plus 3 according to this program, what are we going to print? Not hard. What are we going to print in this case? Take a look at it. 12. Of course it's going to be 12, right? Why? Because, I wish I had a pointer here. I don't. Because the x bracket 3 is equivalent, right, to star x plus 3. Those mean the same thing. Okay? Same thing with the x plus star x plus asterisk x plus 2 equals 5 means put in location 2, or yeah, location 2, the number 5. Okay? All right, so actually, if this was our array, 0, 1, 2, 3, this would be 12, and this would be 5, like that. That's what it looks like. Okay? Not hard stuff. Okay? Just like, yeah, I guess it's up there already. All right. So we actually gave, in the previous program, in the previous one, we gave the array a particular capacity. Okay? We said that the capacity was going to be equal to 10 in this case, right? Which means there's 10 spots there. Okay? We don't have to do that. In fact, later I'll talk more about memory management. This is like delving a little bit into memory management here. Okay? Let's see. Boop, there we go. Okay? If we want to create an array that has 10 spots, but we do it not as you compile it, but at some point during the program, we use the new keyword. And you guys know that already. It's from Comp 11 too, right? OK, use the keyword. And that says, hey, memory system, give me some memory at a particular location. OK? When you use that new keyword, how long is that thing that you've asked for, how long does it last? Yeah. Until you delete it. In the previous program, which means you actually have to use the delete keyword to do that, right? In this program, right? Nope, wrong one. Oh, no, this is a different. sorry, we still use the new here. If I had just said int x10, right, like that, that would be doing it so that it does it at compile time. It tells us there's 10 right when we compile it. How long does that last? Any idea? How long does this one last? Yeah? Until the function ends. Yeah. So, oops. Yikes. OK, so it lasts until the function ends, which is most of the time what you, well, depends what you're doing, but many times that's not what you want. Because it will actually give it back at the end of the function and say, oh, it doesn't, you don't need it anymore. And then your program could end up crashing. So in this case, so we've given it a specific size. In this case, we've given it 10 elements, an initial capacity, right? If we want to add more than 10, in this case, we've had 1, 2, 3, 4, 5. If we wanted to add more than the 5 elements here, can I just start adding over here and saying, give me 4 more, and they're at the end of this? Why not? Why can't I do that? Any ideas? Yeah.
There might be things already there, and you can't just ask the computer to move them.
Exactly. Yeah, exactly. So something might already be there. So in other words, OK, when you use the new keyword and say, I want an array of 10, the memory system says, OK, here's a chunk of 10 spots, and you only get those 10. And if you want to use anything past that 10, you're not allowed to for the whole rest of the program. Right? What you can do is you can ask for more in a bigger amount, right? And then somewhere else, it will give you the bigger amount, hopefully. Right? And then if you use the delete keyword on the original one, it will give this back to be able to be used for some other one. This leads to what we call fragmentation of your memory, which is kind of outside the scope of this class. But it, in the sense that you get these chunks of the size that you ask for when you ask for it, and you can't use anything on either end of them. It's just the way the memory system works. Because you could ask for like 10 and then 10 more, and it could give you the next part, and 10 more, and it could give you the next part. And you could be using all those. And if you want to make this portion bigger, you have to ask for an entirely new section. OK. So we do have to create a new one, or ask for a new one, a new piece of memory, if we are going to expand this array. OK, how do you do it? Well, this always tricks people up. Now, if you have already done the homework, you've gone through this process, and in fact, we put it in the homework. I put it in the homework specifically with these instructions so that you would go through and do it. But in the future, you're going to have to do that kind of on your own. You're going to have to remember all these steps. OK, what are the steps to expanding a dynamic array? Well, let me write this down. Let's do this expansion for part of our memory here. OK? All right. You guys know you're always supposed to erase up and down instead of side to side? You know why? Because if you do it side to side, your butt jiggles back and forth. OK, so sorry, I'm a little lightheaded from the drugs. OK, here's our array. What is our array called right now? It's called X, right? This is the picture we're using, right? It's called X. What's the capacity of this array? In this one, 5, right? 1, 2, 3, 4, 5 spots. Let's put some other things in here. Let's put 7 and 2 and 12 and 15 in there. OK? And if the capacity is 5, and let's say it's all filled up, let's say if these were cards, this would be like cards held, right? Now is when we need to make it bigger if we want to put more stuff in it, correct? OK, so when you know that you have to do this expansion, you probably have the whole thing filled up. OK, that's generally when we need to do this expansion. OK, we already said that we can't just tag on to the end. We have to add another. We have to ask for more space. We generally ask for how much more? Why twice? Any ideas? Kind of a good kind of mathematical reason. Everybody know why we ask for twice as much space? Like for now, I'm going to ask for 10 more, or 10 total, instead of just like 6. We could ask for just 1, right? But then we'd have to expand again, and we'd have to expand again, right? But why would we do twice? Yeah?
Because like the amount of space that you're going to need is typically going to increase linearly, and so by doubling it, you are probably usually not going to need as much space as you have, so you're not going to run out of space.
Yeah, I like that answer. The answer was basically, look, you're adding these linearly. You're adding one at a time. And if you double it, you're going to have enough room to grow as you go. But the other one is that you basically, every time you double it, right, if your program's running along and it needs to keep doubling, you can get big very fast that way, right? And that's kind of the point, is that, so if we go from 5 to 10, OK, we've only gone 5 more, right? But if we double again, that's 20, and then 40, and then 80, and then we start getting big really fast. So it's a way to get yourself to the size that you want very fast. When we get to the end of the class, we'll be talking about these hash tables that I mentioned the other day. And you have to expand those a lot. And if you're using a lot of data, some people will say, hey, if we're going to be using a lot of data, why don't we just create our initial one with like 1,000,000 elements in it, right? Well, why wouldn't, let's take the array as an example. All right, let's take the array as an example. If I start adding numbers to this array, and I started out at 5, OK, and I want to add 1,000,000 elements to it, OK, how many times do I have to double to get to 1,000,000? Anybody want to do that calculation? What would that calculation be? So if we doubled it each time. Let's think of it this way. How about we do this? 2 to the n equals 1,000,000, right? And anybody know what 1,000,000, 1, 2, 3, 4, 5, 6. Anyone know what this is roughly? Anyone have any idea? 2 to the 10th is 1,024. Yeah, what do you think? I think it's 2 to the 20th. Yeah, it's 2 to the 20th is about 1,000,000. I'll put about here. 2 to the 20th is about 1,000,000. If you're adding 1,000,000 things to this array, you only need to double it 20 times. Now, it seems like a lot, right? But 20 times is not that many compared to 1,000,000 elements, right? So doubling it every time is actually a pretty efficient way of getting big enough, fast enough. You don't want to start it at 1,000,000. Because what if you're like, just want 10 elements in there? You don't want to take up a whole megabyte of space, which is what you need to do for, in fact, you'd need 4 megabytes of space for that many integers, right? But you wouldn't want to take up that much space just to hold 5 integers. You want to hold a small amount and know that you can get bigger pretty quickly. This doubling effect does that. OK, off the sidetrack. So what we're going to do is we're going to create a new array of twice the size. OK, so we asked for them twice the size, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we've got an array that's twice the size. And let's call this one like x2. OK, all right. We've now got the one with bigger size. What's the next thing we have to do? Step 2 here. Copy the data, right? That's just going to be a for loop, right? It's going to say, look, copy all these little pieces. We don't need to go to the details about the for loop. But it's going to say copy 7 and 2 and 5 and 12 and 15 in there. OK? And now we've got the data copied. And we've got a space for more stuff, which is exactly what we're looking for. Delete the old array. This is part of the memory management part that we have to kind of consider. OK? We are done with this array. It's dead to us. OK, this array is gone. As far as we're concerned, dead to us. How do we delete an array that's called x in C++? How do we do that? Yeah. Delete square brackets x. Right. OK. Now, pause for a second. That means give back the memory to the system that you asked for at some other time that the system remembers x pointing to. OK, that's all that means. It says, give this piece of memory back. Did it delete the variable x? No, there's no such thing as delete the variable x. People will try to do this. I'll show you what people will try to do after we get done with this. But what you're going to say is you're going to say delete x. And that's going to say x still points to this location. But this stuff is gone back to the memory system to be used in some other part of your program or some other program. OK? That's what the delete says. We will go back over that in a second, too. Then point the old array variable to the new array. In other words, make x point to x2. OK? This is not rocket science either. Right? but I'll put that right there. Okay. Point x to x2, we say x gets x2, like that. We have now changed this pointer to now point to there. Where does x2 point? It points to there. Where does x point? It points to there. What points to this now? Nothing. But it's been given back to the memory, so we don't care anymore. Right? X now points there because this is what we're going to use. This was our array that we're still going to use. Okay? Now x points over there. Now, this is what people always try to do. They say, OK, x now points over there. I'd better delete x2, the variable x2. So they go and they say, delete x2. And that screws everything up. They end up getting all sorts of errors. And they go, I have no idea why I've got these errors. I'm just deleting x2. There is no need to delete the actual variable. Right? People try to do that all the time. But do not do this. OK? You're not going to do that. That doesn't mean anything. First of all, if you wanted to delete that array, you'd have to put the brackets in there. Right? But second of all, deleting the variable, you don't have to delete variables that are not used in a function anymore. Not necessary. OK? So anyway, that was, let's see, that was pointing the old array to the new array and then updating capacity. OK? If we know that this had a capacity, well, this one had a capacity of 5. This one had better have a capacity of 10, which we're just going to say something like capacity equals capacity times 2. OK? And that's your whole 5 steps to doubling the size of an array. Yes?
Do you recommend setting x2 to null?
It does not matter. Yep, you can set x2 to null. We're not going to take points off for that. It's just not going to. It won't really matter because if you don't use x2 again in the function, then it won't matter anymore. Yeah, good question though. Yes.
Why do we create a constructor, a destructor that deletes the array if we do it in the expand function?
That is a great question. The question was, wait a minute. In our destructor, we also have a delete for the variable. OK, let's walk through this. Let's say this was our initial one. Where did we create this one? Constructor. OK, so this piece of memory existed at the beginning. And then we went through this expand process. And we deleted this one. And now we've got this one. OK, let's expand it again. We're going to delete this one. And now we're going to have a bigger one. Right? Let's say it's this one that we've now got here. OK, we get to the end of a program. Have we deleted everything that we created? There's one thing left that we still need to delete. So this is what the destructor does. It takes care of this last piece.
And so how do you call that if it's the same name as the constructor?
You don't call it. You never call the destructor. Yep, it does it by itself. When the class ends, the compiler knows, OK, make it so that this destructor gets called. So it happens automatically, and that's that. Yeah, good question. OK, other questions on expanding these things? Anybody else? OK, you'll see this a number of times, this pattern, a number of times in class. OK, for arrays, for things called circular queues, for other things as well. OK, so we'll do this more. And I haven't exactly decided whether we're going to do the first lab or not. Labs start next Monday, by the way, on this stuff or not. I'll probably skip it because you're just doing it for homework, so I might as well skip it. OK. All right, so there's the whole thing at once. Right? We've expanded the array. We've created a new one. We call it expanding. But really, we've created a new one, copied everything over, and deleted the old one. OK? And then new x will get removed at the end. OK? You can look at these notes online if you want to. OK? All right. So what are some more list functions? Right? So in the interface that you've got for your dynamic array, right, you've got these things called insert at head, insert at tail. Right? Insert at head would put it here. Insert at tail would put it here. Right? Actually, not true. Insert at tail would put it at the last, like the position after the last one that's actually in there. OK? We've got insert at index, which says put it at a particular place. OK? You have to be a little careful with this. You can't do something, well, for our interface, you don't want to do something like this. Right? What you don't want to do is you don't want to say, how many cards are there right now? If these were cards. 0, right? Okay, you don't want to put a card here. We'll just call it card 1. You don't want to put it here and then put another one over here and say there's 2 cards in there. Because these guys are bogus, and you don't want that to happen. You want to put them next to each other. We allow you to put we allow the function insert at index based on the fact that I had to figure out some way to do a sort, and that was the easiest way to do it. So it's probably the only real legitimate way to do it. But you don't want to make it so that your interface breaks some other things. Because now, if we said there were 2 elements in here, this one and this one, we don't know that it's here and here. We would think it was here and here. Does that make sense? It's a little bit, you have to be a little bit careful with some of these functions. Okay? I probably could have defined that a little bit better in the interface, but you have to be a little bit careful. Okay? Let's see. Remove from head, remove from tail, remove from index. Right? A couple different things going on here, right? If we have, let's use this one here. Let's still x. Well, this is now x. Okay? If we say remove 5, what that would do is that would go along and it's, or well, not a good example. 0, 1, 2, 3, 4. Oh no, remove 5 would be an example. If you do remove 5, it will go, is this 5? Is this 5? There's a 5. Remove it. Okay, do you see how that works? That's going to be remove 5. You've also got remove from index. If you did remove from index 2, that would remove this one. It would also remove the 5, right? It wouldn't remove the 2. You got to understand the interface in that sense a little bit too. Okay? And when we remove this 5, what you have to do is you have to move everybody else back into that position so that we know that the array is tightly packed. Right? So 12 would go there, and 15 would go there. And you would have to also update your number of cards that you have, for instance. Okay? All right. Questions on that stuff? If you've already done most of the homework, then you're good to go on this stuff. Yeah? Zoe?
For remove, like from index, you
Yes.
want to like store the cards that you remove somewhere, or can you remove all of them?
It depends. Well, I forget exactly what we said, but I think when you say remove an index, you actually return the card. But that's all you have to do. You don't have to store it anywhere else.
So for like
Nope.
remove from 10, then you don't really have to remove anything.
You just move everything else back and return. You have to keep a temporary one of the one you're going to return it. But other than that, nope, you don't need to do anything else. OK? Yeah. What else? Other questions about this stuff? Yes?
How can you do remove from index without a parameter? Telling you which index to use?
Oh, you're right. That should have a number in there. Absolutely. Yeah, thank you. Remove. It should be removed from index and then int index or something. Good. Good call. Good catch. Not on purpose, unfortunately. Thank you. Anybody else? OK. All right. So behind the scenes, we've already talked about this. Behind the scenes, you're going to write all these array methods. Next week, you're going to write all the linked list methods, OK, that are going to do this. Okay, some are very trivial. Some of the functions are very trivial. Some are a little bit more advanced. None are too tricky. But I didn't want this assignment to be too bad. The linked list ones get a little bit trickier. Next Monday, when we talk about linked list, we'll talk about some of the pitfalls in dealing with linked lists. All right. I know you've done it before for Comp 11, but I found that most people, given even what they learned in Comp 11, couldn't go write a linked list right now that would work right. Why? Because there's lots of little tricks you have to do it. Some of you could, obviously, but it's trickier than you might remember. Or maybe you do remember and you don't want to relive it, but too bad. OK. All right, so we already talked about some of the methods that we've implemented up here. OK, we actually already talked about testing some of your code, too. So I kind of already went through this. But how about you go testing the insert at tail? Well, you can write a new main function. We talked about that. Only write enough to test that function. Sometimes that's not possible, right? If you want to insert at tail, you have to have other things inserted first. Or you could insert tail, insert tail, insert tail. But sometimes it's not possible to just write a test that does just one thing because you need setup, right? What you should do is do all the setup testing. Once that's working, then test the other stuff. Okay? Just write enough tests, though, to get to the part where you need to do the test function. OK, what is this? Let's see. This is your one of your tests that we kind of showed you this before, right? Insert at tail, print list. So this would be testing insert at tail, right? It inserts at the tail, then it prints the list, and then it sets the suit to a 10 of hearts and from an ace of diamonds, and then inserts at the tail again, and then prints it again, right? So what should this print when what should this actually output to the screen? What do you think? Here's something I'll do during the class a lot. I'll say, ask your neighbor. So talk to your neighbor and say, look, what is this going to print out onto the screen? Go ahead. You might not remember what print is doing, but get close enough. OK. So here's what we've done. Let's just walk through this a little bit. First, we've created your linked list, your list dynamic array. OK? We've created some list dynamic array. OK? It happens to, I think the initial size would be 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. OK? So it would create that. And then it would create what? A card of what card is that? Ace of diamonds, right? And what I'll do is I'll just write it here and I'll say, look, this card is going to be ace of diamonds. OK? And oops, there we go. This is the ace of diamonds. So it's going to create that card, right? And then it's going to insert it at the tail. Where is the tail of a 0-element list? It's at 0, right? So it's going to insert that ace of diamonds here. And I'll just do this. It's going to insert the ace of diamonds like that. OK. And then print. And what's it going to print out? Ace of diamonds, right? OK. Ace of diamonds. That's the first print. However it prints that. Maybe we don't remember exactly, but it's going to print the ace of diamonds. OK. Then it's going to set the suit of this card. So it's actually going to go and change the original card here. And by the way, if you noticed in the homework, there's these things called copy constructors and operator equals overloads and things. You do not need to worry about that. But that's because what we need to do is we need to make it so that when I say something like, this location gets the card, I don't want this location to point to the card. So when I change this card, this one also changes. I don't want that to happen. We'll get into more details about that later, but that's not what I want to happen. OK, so it's going to set the suit to heart. Actually, it starts as ace of diamonds. It's going to set the suit to a heart. And then it's going to set the rank to 10. So it's going to be a 10 of hearts. And insert at tail is, where's the tail now? After 0, right? It's going to be here, actually, is where it's going to put it, right? So it would be 10 of hearts. And then when you go and you print it again, it's going to print ace of diamonds, 10 of hearts, something like that. OK, that's not that hard. Does everybody get that when you're looking through it? OK? All right, this is how you would do a little test to do this. OK, and if it prints ace of diamonds, 10 of hearts, you're probably in pretty good shape. Although you might want to try it for more cards than just 2. OK. All right. We already talked a little bit about this memory management a little bit before, right? But let's go into just a little bit more detail about this stuff. OK? One of the issues with learning C++ is that you have to do all this memory management yourself. If you were learning a language like Python or learning a language like, I don't know, JavaScript or Ruby or something like that. All this memory management stuff is handled for you, which is actually kind of nice. But we're doing C++ because we want to understand a little bit more about the actual machine underneath the computer, in the computer itself. So we kind of have to do this. And C++ allows you, and in fact makes you, do a lot of this memory management yourself. Okay? When we do the top part, we already talked about this. When we say card, hand, 10, that gives us an array of 10 cards, okay? And that's called a static declaration. It happens to be put on this thing called the stack. Now, later in class we'll talk about, in a couple weeks we'll talk about stacks in general. But the stack is a particular piece of memory that your program gets when it starts out. It says, here's all the memory your program gets. It's such and such big. And if you want an array of 10, it puts that array of 10 in that part of memory. Okay? That lasts, as we said, through the whole function, and then it's gone at the end of your function. The other one gets from a totally different piece of memory called the heap. Why is it called a heap? Well, it kind of seems like a little heap of memory that you're grabbing from and picking out pieces that you can use. When you do the new card 10, that grabs from a totally different place in memory and says, here's your little piece. You can have it for the whole rest of your program. Not just the function, for the whole rest of your program. Okay? And this is the one that we need to actually delete. Okay? That's what's kind of going on kind of under the covers. Okay? The stack allocated, deleted when the function ends, and the heap allocated, and you're the one responsible for it. Okay? Anytime you use the new keyword, the piece of memory must be deleted at some point. Now, we've already talked about this. Like, when does it get deleted? It gets deleted when you either replace an object with some other one, or in the destructor when you've only got one left, generally. Later we'll talk about, like, if you've got a whole structure of things, your destructor needs to go and delete every little piece, which is a little bit different. But anytime you use a new keyword, that piece of memory has to be deleted. Okay? What does that mean? If you replace the other, this is exactly what we talked before. So the question that came up earlier was led right into this, right? If you replace an array, you delete it right then. But you also delete it in the destructor because there's always one piece left over that you've been using until the end of your program. Okay? Destructors and constructors get called automatically. Don't call them yourself. And that's how it actually works. Yes?
You have to denote the destructor with that little squiggly.
Yes. Yeah. When you, I didn't have an example up here, but yeah, when you say for the card, for instance, when you're defining it, right, you would say tilde card, right, and that means, oh, that's the destructor. And then when you actually put it into your class itself, you would do something like this. If it's a card class, you would do card : actually, let me think about this. I believe it is, yeah, I believe it's card : tilde card, like that. Yeah, and that's it's either that, or it either comes there or there. I forget exactly which one, but you can look in the program to see. But that's when you do it. You just declare that, and that is called the destructor. Okay. All right. So memory management is we can actually test to see if our programs are what we call leaking memory. It means we didn't give back everything that we requested. Okay, and we will test this on your homeworks. Like when you provide your homework, Provide will actually run a test called valgrind. And I don't exactly remember what valgrind stands for, but it's a program that checks and it keeps track of everything you asked for and keeps track of everything that you've given back. And it gives you a little report that says, hey, you didn't give back this amount of bytes at the end. You lose. Right? And we'll take points off for that if you don't. So you always have to check these things. Here's how you run valgrind. In fact, let me show you this. Running valgrind is pretty easy. You just type, actually that's wrong. You just type, you don't type the dot period. You actually just type valgrind without the dot period. There we go. All right. You type valgrind and then dot period homework. So you basically, instead of typing dot/homework1, which is your program, you put valgrind in front of it, and that's the output that you get. Okay, don't worry about the numbers along the side. That's basically for bookkeeping if you want to run it into other programs and things. But this is what it tells you, right? It says, hey, look, when your program stopped running and when it exited, it had 88 bytes left in one block. Okay, and it says you definitely lost those 88 bytes. In other words, you didn't return them to the memory system. Okay, you can actually rerun this again and get more details if you want, but if it says something like that, it means that, hey, you didn't give all your memory back. And you need to go back through your program and say, where did I use new? And and why didn't I give it all back? And what did I do? Is my destructor wrong? Is my expand function wrong? Right? And you can run it just like that. Okay, what you want to see is the following. You want to see this. You want to see heap summary. In use at exit, 0 bytes and 0 block. All heap blocks were freed. No leaks are possible. Okay, that's what you're looking for. You're striving for that, right? Let me show you this in action. Okay, let's see. Are we still connected here? No, we're not. Connect again. Okay. Okay. If you're really sneaky, you'll look at this if you haven't done your homework yet and see the solution, but don't pay too much attention. Let's see, list, dynamic array, CPP. OK, so here is, let's see, there's our destructor right up here. Yeah, by the way, you put the tilde right before the actual function, the actual destructor name. OK, and here's what it says. It says delete the list. This says if cards actually exist. You probably don't need this part. But anyway, if I comment this out, right, my destructor no longer has anything in it. Okay, and if I make it and run valgrind on it, right, whoops, oh, not valgrind, valgrind. There we go. If I run it on it, it gets all this stuff. It actually runs your program. So there's the output of your program. It actually runs it. And then it says, look, in use at exit, 824 bytes. Uh-oh. Right? You lost all these memories, or all this memory, because you didn't return it. What's that? Also, all these memories you've lost, yes. OK? And so you go back and you go, where could that have happened? Whoops. Where could that have happened? That could have happened in my destructor. Oh, yeah, look, I deleted that, or I commented that out, right? So, whoops, uh-oh. There we go, hang on. There we go. OK, so now it's there again. I can make it again, and I can run valgrind on it. Actually, I can run make on it first. Make, and then run valgrind on it. And hopefully this time it says, there we go. OK, all heap blocks were freed. OK, so you should be running this before you do your provide. Although provide will run it for you and tell you that your test failed for the valgrind as well. OK, questions on that? Yes.
So obviously, if it was a huge, huge program and you needing to be using lots of different bytes in memory at different times, you want to be making sure you're clearing them. But
yes.
Just for our purposes at the moment, is that physically affecting the computer? Like, is it?
Yeah, that's a good question. Yeah, is it really affecting anything? Well, not now, right? But for instance, last semester we had a final project that was, I don't know if you guys heard about it from other people you know in the class, but there's this project called Song Search. And it uses a 250 megabyte data set. And when you're using it, it uses about between 2 and 4 gigabytes of memory. And if you're not freeing things as you're going through, you'll all of a sudden instead of 2 gigabytes, you'll do 4 and 6 and 8 and 12. And all of a sudden, you're using really significant chunks of memory. They won't even run in some computers. So yeah, so for our programs, no. But I'm teaching you how to do it so that when you write bigger programs, it'll work better. Right? Yeah. Other questions? Yes?
Will valgrind tell you, like, so in the line that you say, like, a new array, will it tell you, like, that's the, like, the literal line where you create the memory address that you use?
Will it tell you? Sometimes it will tell you, yeah. Let me try it again here. OK, let's make it, and then clear, and then run valgrind on it. Oops. Clear, and then run valgrind on it again. And let's see. Does it say in this one? In this case, it does not. Sometimes it will tell you. I think if you do the leak check equals full, let's try that. I think if you do that, valgrind dash dash leak check equals full. Let's see. Okay, there we go. Look, it says here's where it was lost from. Right? So it doesn't tell you where you didn't delete it because it has no idea where you didn't delete it. But it tells you, hey, you lost it right from here. You lost it when you did an insert at tail. Well, what happened here, right? Oh, there's an operator new on this line. Let's see, dynamic CPP line 220 in your expand function. You had a new. And so you go look at that and go, wow, did I delete that one at the end? No, I didn't. Right? So yeah, with the extra information, it'll tell you. It'll do a good job of telling you. So yeah, good question. Anybody else? Yes? Oh yeah, well, it tells you what to do, but it tells you if you don't type it in, but it's this. It's valgrind dash dash leak dash check equals full, and then your program name. Okay. All right, what else? Okay, so I believe, let's see, where are we here? I believe, yep, that's it. So there's some advanced reading in here if you can go look at that. And then there's some references there. If you have not yet been enrolled in the class, you should probably see me, and hopefully you'll have an ad form or we can get that for you or whatever. Don't forget to sign up for labs tonight, 6 p.m. They start next Monday evening. And let me know if you have any issues. Homework's due Friday. See you guys later.